Hello and welcome to Simplified. My name is Gurjot
My name is Michael.
and this is episode 10. Today we have with us someone finally from my home country, India, Professor Vijay Natarajan from the very prestigious Indian Institute of Sciences, Bangalore. Professor Natarajan, thank you so much for joining us today.
Hi guys, wonderful initiative. Yeah, glad to be here.
How are you doing? What's the weather like in Bangalore?
Today is good. Thankfully, we have rains. So
Yeah.
yeah,
Well, that's nice to hear because the weather here hasn't been all that great for the last month. It's all of April. It's been snowing and raining.
It's becoming winter again.
okay. So it's the other way around. We're just glad that the temperatures dipped a little bit. It's been quite hot, unusual for Bangalore.
Yeah.
But
Now, to start things off, can you give us a 30-second pitch of what you do and why it's cool?
Okay, sure. So I am interested in understanding data. So the way I go about doing that is creating pictures out of data and allowing people to both explore the pictures and kind of interactively query the pictures to understand interesting patterns in their data, make hypotheses, and then solve underlying scientific problems.
So when you say understand data, what kind of data are we talking about?
So that's kind of an interesting question. So our research community, the visualization community, we like to categorize ourselves into so-called InfoVis, information visualization, and scientific visualization communities. So this classification is based on the kind of data, right? Um, so if the data is geometric in nature, right? So let me give examples. If the data is, let's say, temperature in the room that you're sitting in, or maybe temperature across the globe, or for example, the density of fluid as it passes through some chamber, or pressure in a room. So those are spatial in nature. So you have pressure at every point, and the data is sitting over a geometric domain. So that kind of data, we call it in this community, we call it scientific data. The data is not really more scientific than the other kinds of data. It's just that the data comes typically from science engineering disciplines. Right? So to contrast, you have data that need not have a geometric context. So, we see such data in day-to-day lives, right? So the emails that you get, or for example, census information, right? So population information and things like that. Other kinds of statistics that you get bombarded with in the media every day, right? Or for example, the kind of, so if you have a web page, then who is visiting you, right?
Yeah.
Or social networks, right? So there's no geometric context there. It's just connectivity. I'm connected to you as a friend. You're connected to someone else as a friend. We are not. There's no spatial context here. So the kind of visualization one needs for these two different kinds of data is inherently different. So I work with with scientific data primarily. So data that comes, let's say, from imaging devices. So our CT scans, MRI scans, and then more. These are kind of scans that many of us have gone through. Right, as you go older, maybe not you guys, but also other similar imaging devices, right, are used in science disciplines like electron microscopy,
Yes.
which allows you to look at the fine resolution detail. Right?
Mhm.
So such scanners and medical or imaging devices give you data with a spatial context. and I'm interested in kind of understanding patterns in these data. Another source of data is simulations. Often we are not able to do measurements. So, for example, I work uh, closely with climate scientists.
Okay.
So, in order to understand, for example, kind of, one of the recent problems that that I work with, looking at is the monsoon in India. It's considerably one of the hardest problems because there are so many factors that affect the monsoon in India. And in order to understand this, you need data. So you need data in terms of wind speeds, wind velocities over the domain, over the region, not just India, but the whole globe. And, you also need temperature, pressure information, precipitation information over over many years, right, decades. And this data cannot always be measured. Right? We don't have enough measuring instruments or even the technology to do all kinds of measurements. So we rely on simulations. So from first principles, you model the physics
Yeah.
and look at the circulation models, and from that you start from some timestamp where you're able to. So you assume some initial conditions, and then you run the simulation forward. You of course you fix the simulations. You correct the simulations is the right word.
Yeah.
You correct the simulations with whatever measurements you have. And that also gives you, for example, it gives you the temperature over the land for hundreds of years.
Yes. So yeah, that's a wide variety of sources you talked about. I'm pretty sure the use case for visualization in different areas is different. Could you emphasize on that? So if we talk about the monsoon problem, so what exactly do you visualize from this data? Do you create like a map of the globe, and what is it that you do?
Right. So yeah, I'll try to answer that question first, and then maybe take off from there. So in the particular case of climate science, there are a couple of problems that I have looked at. I mean, I'm a computer scientist. I'm no climate scientist,
Yeah.
so I start with the problems that the climate scientists are interested in, and try to see what kind of technology, what kind of algorithms will help them solve their problems. Right? So one of the problems that they are looking at currently is, well, this was in the past. So is how do clouds move, right? So clouds are very difficult to handle on the computer because I mean, there's no clear definition of what a cloud is. You don't know where the cloud begins and where it ends. There's no clear boundary, right? So, so one of the problems they are interested in is tracking clouds over time.
Okay.
So why is this useful? This clouds, and often clouds as in rain-bearing cloud, right? So they are indicative of rainfall.
Yeah.
Now, especially if two cloud systems hit each other, right?
Yeah.
Have catastrophic events, right? So you have huge rainfall events. For example, there are at least two such instances that happened in India over the past decade. One in Mumbai about 10 years ago, when there was a huge amount of rainfall on a single day.
Yeah.
And more recently in Chennai, when there was multiple such events happened and there were a lot of floods.
Yes.
So for such specific phenomena, so the tracking of clouds is very important. But cloud tracking is also more important to study long-term behavior. So to see if there are any repeating patterns that happen. Like, for example, monsoons in India happen always from May to July.
Yeah.
So what happens? How do the how does the monsoon proceed, right? So in order to be able to answer such questions, in order to understand the science, one has to know where the clouds are coming from and where are they heading and where do they disperse.
Yeah.
So for this reason, cloud tracking is important, and we leave it at that. We don't really, as computer scientists, I don't understand how the information about the clouds is used to understand weather patterns and climate science. But I help
With the tracking and collecting data from it.
Yes.
So you mean your focus is more in transforming this data into something more comprehensible, such that computer scientists and other people can make predictions?
Exactly. So I don't do predictions myself, but I'm interested. So what the kind of techniques we develop is starting from existing simulations and existing satellite-based measurements, extract clouds,
Yeah.
and in a interactive visualization framework, right? A visual framework where you see the clouds, show the tracks of these clouds, and allow for different kinds of queries, so that the user, in this case, the user is a climate scientist, allow them to make
Yes.
pose different kinds of queries, and for example, the kind of queries they may be interested in is, for the duration of 2000 to 2010, show me the tracks of all westward moving clouds. And once you see such this query A has to be answered quickly, and it has to be and B, it has to be answered in a visual form, right? You don't want just the data to
Yes.
be listed, right, as text. You want it to be displayed in a understandable form. I cannot just display all the clouds; that would clutter the entire screen. I would
Yeah.
have to come up with interesting representations of the cloud so that it can be displayed on the screen. You can imagine over 10 years there are.
So what you see is like a map of India with a representation of the clouds that are moving
Correct.
westwards.
Correct.
That's what
And
you
then,
create. Okay.
But in addition, it's very important to answer these queries, right? So, or to allow for these queries to be posed in the first place, right? So then they can look at interesting patterns from there.
Are you trying to come up with a general process of analyzing this data, or are you analyzing individual data sets?
Right. So I started off by talking about this because this is a specific problem in a specific application domain. So the solution is also catered to this particular problem, right? But the underlying technology, like how do you detect these rain-bearing cells, these clouds? How do you track them? Right? Those are generic problems that we are interested in. So we have over 10 years, we have designed fast algorithms to detect these cloud-like structures. Right? So for us, these are not clouds per se, but these are just some volume elements, right? Some volumetric objects that we are tracking over time. Now, how do you define these volumetric objects given just pressure or temperature? And then how do you track them over time? How do you display them over time? Those are computer science questions that we ask.
Yeah.
So that's the kind of technology that we have developed in order to answer questions. For example, in the case of monsoon, in the case of cloud tracking, these volume objects were clouds. But in other applications, for example, if you look at let's say the study of fluids, right? So many people are interested in studying fluids, like people in aerospace, people in automobile industry, they're interested in studying fluids and how they move. So here again, such volume elements come into play. So many of the turbulent structures can be represented using some of these volume elements. Now again, you are interested in tracking these volume elements over time and see where they merge with each other or split each other. So the same technology is used in those applications as well.
Yeah.
Right. So that's essentially out of
That sounds.
the underlying work that goes in our But then we look at specific applications. We don't look at all applications because working with a different domain takes a while. Right? So I primarily have worked primarily with climate science folks at IISc, so with folks looking at biological problems. So people studying proteins.
Yeah, so I'm assuming also a major role that you play in this is, I mean, I'm pretty sure the climate scientists themselves could figure out one way of visualize some or the other way of visualizing the data they have, but you kind of give them something that's maybe easier and also much more faster, isn't it?
That's correct.
I mean, speed must be like one of the best things you do. You make data visualization really fast, being computer
That's
scientists and better at algorithms.
right. So speed is something we are always looking at. Yes. One, it's a very, I mean, it's probably the simplest to quantify and claim that we're doing good.
Yeah,
But we are equally interested in designing visualizations that are useful, that are effective. Right? So this is a little bit more difficult to quantify. So
yeah,
you essentially need committed users, right? Committed collaborators who will work with you and use the system or use the algorithms that we develop in their work. Right? So, and if they are able to successfully use it, then we call our systems as useful. And if they're able to use it to answer their questions quickly,
yeah.
then we say that our system is effective. So there are two, both speed is important, but I think equally important is how effective is.
Yes, I mean, speed is important because the size of data is increasing much faster than computational levels are increasing, right? I mean, processor speeds can only follow Moore's law, but data seems to be growing at a much larger pace. Am I right?
That is true. So there are many of these resources that are actually growing at rapid pace, but something that's not growing is, for example, the Windows size, right?
Yeah.
Or our cognitive capabilities is not really increasing. So even if I can compute, for example, million clouds, right, within a fraction of a second, I cannot simply display all those clouds on the screen because the human is there, right? So the human
Yeah.
cannot comprehend all that information. So what is very important is, that is a major constraint for us. Right? We will have to eventually present the data in a form that is palatable to the
To
user,
the end user,
so
yeah.
that they can take to the end user, yes, so that they can make
So,
effective decisions.
do you think machine learning and artificial intelligence would also play a very important role because maybe machines could understand data much better than human scientists on the other end, right? I mean, you wouldn't have
That's quite
to make a dumbed down representation of the data. You could just throw the entire data out, and the machine could get it.
that's perfectly right. So that makes sense. With better machine learning algorithms being available now, that's a very valid approach. But one of the situations where visualization plays a very important role is when one does not know what, so as a scientist, if I don't know what I'm looking for, right? So I have data and I know there are some patterns there. I don't have a definition of the pattern. I also, I only have, based on prior work, I know about related data. If this particular data is fresh for me, I don't know what it contains. Right? So the way I find interesting patterns in there is by exploring. So in this situation, it becomes a little bit difficult for a machine learning approach to help. But once I'm able to explore and identify possible interesting patterns, then I could use like a data mining algorithm or any other classifier or, right, so or any machine learning algorithm to to help me find all such patterns quickly. But exploring and identifying what is interesting um, requires the human. So even here, the machine learning kind of approach can help, um, but it will always require some kind of a model. Right? So machine learning algorithm will require a model. Unfortunately, in this situation, it cannot learn from prior data, right? Because the data that you are generating is new and possibly the first of its kind. Right? So the kind of approaches that have been used to recognize faces, right, to recognize speech and so on. Right? So they rely heavily on large data sets. So all the what's hot now, deep learning, it relies heavily on availability of large amounts of data. So unfortunately, in this situation, we have one data set, right? So the human is required.
Yeah.
Like I say.
Now, would you draw a clear distinction between a scientist like yourself and like the modern day data scientists, people who are employed by, say, Facebook and Google to look at analytics data of user interaction and stuff? Would you say there's, like, apart from uh, on a very general scale, that they are looking at data and trying to infer something from it, and you're doing the same thing, but there's a clear distinction, like you said, you look at scientific data, and user interaction data is not exactly scientific in that regard.
So there is a lot of overlap, right? So visualization does play a very important role for a data scientist, right? Because it is a part of their toolbox. So the way I'm an academic researcher. Right? So my goal is to provide better methods, better algorithms, better technology that can sit into their visualization toolbox, right? So into the visualization toolbox of a data scientist, into the visualization toolbox of a domain scientist, right, of a climate scientist, or of a biologist, or of a physicist. So in that is probably the difference between what I do and what a data scientist would do. A data scientist is interested in understanding everything about that particular data, whereas I'm interested in developing methods that could be used by data scientists. Right? But my focus is only on visualization. So in that sense, there is some overlap.
Generally speaking, how would you describe your approach to new problems? Say you're given a new problem to solve. What's your general first step?
Okay, kind of hard question to answer. This is usually no recipe, right? I mean, I don't know. Okay, so I work on both theoretical problems and working together with like domain scientists. So the approach is a little bit different from the two, if I have to generalize. So if I'm working with let's say I'm working with a climate scientist on, say, the cloud tracking problem, my first few steps would be to sit down and understand what they are doing. So this would be over discussions, reading papers where I don't understand beyond the first and second paragraphs, right? So understanding their language first, and then once we understand the problem, then the next step would be to get some quick visualizations out using existing off-the-shelf software. So this is also to understand their problem. Right? So in the first stage, we try to understand their problem by reading it. In the second stage, we try to convince them that we have understood their problem by coming up with simple solutions. Right? And then, so then I guess we sit down and like design a novel solution for them. I think that is as probably course description, but the finer details really differ from one project to the other.
Yeah, that's all really good.
All right, as a closing question, we would like to know what's on your bookmarks bar on your browser.
I don't use bookmarks anymore. So if I go back and look at my bookmarks, they're all from my PhD days.
We find it so strange. I mean, the last couple of interviews we've done, people don't use bookmarks anymore. It just doesn't make sense to us because we still actively use bookmarks.
Okay, so even on my, so I don't use bookmarks, search, but more importantly, even on my, I use a Mac. I don't use folders much.
Okay.
Are there specific websites you frequently browse?
Yes. So I have my library on Google Scholar. The library is automatically populated with my papers and papers of interest to me.
Mm-hmm.
So I look at that for recent updates often. So and I also look at journals and conferences. But out of besides this, no specific tools that I look at. Maybe now I will add simplified.
Yes.
Yes, that'd be
Yes.
something then you can tell everyone about it. Well, that's fantastic, Professor Natarajan. Thank you so much for joining us today, and we wish you good luck with your visualizations.
Thank you very much. Thank you very much.
Thank you for listening. If you liked it, we'd really appreciate it if you shared it and gave us your feedback. We publish a new episode every week. For more details, visit our website simplified.xyz.